Okay, so week 4. And the first thing we're going to do is we're going to talk about the marginality principle, the principle of marginality. And what this says is that basically you've got to be careful when you're choosing your models. You can't just throw anything out. So the basic rule is if I have an interaction term in my model, all implied lower order interactions and main effects must also be included, and that includes the intercept. So, for example, imagine I fitted a model and I decide that I have categorical variables A, B, and C, and I've decided the three-way interaction term A, colon, B, colon, C is to be included in the model. Once I do that, everything that sort of involves A, B, or C is involved. So I've got to have the two-way interaction terms, A interaction B, A interaction C, B interaction C. I've got to have the main effects, which is A, B, and C, and I want the intercept in there as well. Okay, so that's the rules. Why? Well, first of all, two things. One, we need to impose constraints on the parameters to achieve identifiability. That is, that there isn't like an infinite set of solutions. And if we maintain the marginality principle, then the constraints won't affect the model. Even though you might have different reparameterizations, they're still at a deep level the same model. Okay? Now, you don't often have to think about this. R will do it for you most of the time. So for example, if I do A star B, it will automatically go, oh, you want an interaction, so I'll have everything you need up until and including that interaction. So you get 1 plus A plus B plus A colon B, where A and B are your main effects, 1 is your intercept. So as soon as you do that, it takes that into account. And in fact, if you start removing important terms, it will readjust under the bonnet the design matrix to make sure it's still safe. And at the end of this, I'm going to crack up R and show you some examples of this. So if in that case I remove A, the main effect, it will instantly go, oh no, you've violated the marginality principle. So now what I'll do is I'll remove one of those constraints I had in the first place. So if I try and do that, it will remove another constraint to make up. It's like as soon as you take something out, like A, it basically adds something in by removing a constraint. So, and if I go A colon B and that's it, and I don't put anything else in, it will remove all the constraints. The only problem is, in this particular case, and this is why you have to be careful, and we'll see it in a second, now your model matrix are not linearly dependent because you've really overdone it. The same happens if I have factors and covariates. If I go A star X, it goes right. In this case, I need A intersection X. A is a factor, X is a continuous variable. So because it's an interaction term and I'm keeping it in the model, I'm going to need A and X and obviously intercept. We have a weaker version, which is for polynomial regression, which we don't enforce every time, but generally, if I have a cubic term, for example, then I should include all the other lower orders. So I should have an intercept X, X squared, X cubed. The only time I personally don't include them automatically in there is if it's a particular model that I've been given by someone, like a physical model. But often, if I was just generally fitting a polynomial, I would try and include all the lower order terms as well. Because it just means you've got more flexibility and you're going to get a better fit. So there's your principal marginality. The slides don't really help. What we're going to do now is we're going to go over to R and have a look, because I think that will help us. So I will upload this as always. We've got our marginality. I'm going to create us some data to start off with. Oops, as always, I always forget to run my packages. Nice, let's run my data frame. So what I've got in this data frame is I've got two factors, A and B, with 3 levels. So A has got 1, 2, and 3, and B has got 1, 2, and 3. I've got a continuous variable, X, which has the values 1 to 9. So let's imagine I start off with a standard thing. We do the model matrix, so we say I'm going to fit a model where I'm just going to have my predictor is the factor A. Make me my design matrix. I do that with model matrix. And here is my standard design matrix. We've seen this a couple of times. Basically, you've got your intercept. It's used reference level, so level 1 has been set to 0. So this column is a 0 if you're anything but level 2, and a 1 if you're level 2. And this is a 0 if you're anything but level 3, and a 1 if you're level 3. So there's your standard thing. Imagine now I try and remove the intercept, and I will go, you're breaking the principle of marginality because the intercept should be there. I need to make up. And it does. It goes fine. I had that extra constraint that basically alpha 1 equals 0. You've removed the intercept, so I will make up by removing that constraint. So as I remove a term, R is making up by adding in a term, and it added in a term by removing that constraint, in this case alpha 1. So now it's taken into account. Let's do similar sort of thing. This time I'm doing up to two-way interactions. So I will have my intercept, my main effect. So my main effect A is represented by 2 columns. My main effect B is represented by 2 columns. And then we had our interaction terms, which we talked about before. What happens if I go, well, actually, let's do that, but remove A? Well, now what it does is it goes, you removed A, I will remove some of those extra constraints. So if we look here, what suddenly appeared is, see here you've got A2, B2, A3, B2, and A2, B3. In all of these, you don't have A1, but I've removed A, so suddenly where is it? Am I getting this right? Sorry, I don't have B1. So it made up by introducing back B1. So you see up here, I've got A2, B2, A3, B2, B3, B3. I've got B3, B3, B2, B2. But we lost 2 columns. It's made up by basically indirectly giving me back 2 columns by letting in the B1. Okay? So as soon as you remove it, and you'll notice in this case that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've still got that 9 columns. So it basically went, nah, I want to maintain that. You've removed all the columns that were just A on its own. So I will add in extra interaction terms because you didn't say I couldn't do that. So I'm going to do that. What if we just do the interactions on their own? Here R does break a little bit because now there's no columns for just A or just B. They're all interaction. But if you look carefully, if I take all these last columns here and add them together, if I add each of these vectors together, you will basically get 1 plus a load of zeros, which is 1, a load of zeros plus 1, which is 1, a load of zeros plus 1. If I did that, you would get this. So this case, by giving this model matrix, you've actually completely over-egged it. You now have the columns are not linearly independent. This wouldn't fit. Let's see what happens when we have a factor and a x. So here we've got our 2 columns for the factor. We've got a column for our x. And here's our interaction terms. If I now try and remove that x, like that, it again tries to make up, and it goes, you've lost x, so fine, I've lost a column, I will add a column. The one that's missing here is a1x, so I will add in a1x. So that's it really. Think about it. Anytime you have interactions, you need to leave the terms in. If you try and remove them, sometimes I will let you, but sometimes it will sneakily try and get around it because it doesn't like when you mess around with that sort of thing. But key idea, if I have interaction terms in my model, anything that contributes to the interaction term should stay. Okay? See you next time.